In this lecture, we construct a square root function that is differentiable or analytic within a subdomain of the complex plane. Let z be equal to x plus I times y, where x and y are real numbers. Let r be equal to the absolute value of z, so that r equals the square root of x squared plus y squared. Let theta be the principal argument for non-zero z, so that minus pi is less than theta, which is less than or equal to pi. And so, if z is non-zero, z equals r times e raised to the power I times theta. A complex number w is the square root of z if and only if w squared equals z. We can write w as either the square root of r times e to the power I times theta over 2, or the square root of r times e raised to the power I times the quantity theta over 2 plus pi. E raised to the power I times the quantity theta over 2 plus pi equals e raised to the power I times theta over 2 times e raised to the power I times pi. E raised to the power I times pi equals minus 1, so that just like positive real numbers, each square root of a non-zero complex number is the negative of the other's square root. 0 is the only number with a unique square root, which is 0 itself. Since each non-zero complex number has two distinct square roots, we can construct two square root functions called branches of the square root of a complex number. We define the first square root function f sub 1 of z as the square root of r times e raised to the power I times theta over 2, and the other square root function f sub 2 of z as minus the square root of r times e raised to the power I times theta over 2. Since f sub 2 equals minus f sub 1, we will work mainly with f sub 1. We claim and prove that f sub 1 is discontinuous at negative real numbers and at 0. Let z be a negative real number so that z equals minus r and its square roots are I times the square root of r and minus I times the square root of r. Let zeta approach z from the second quadrant so that the principal argument of zeta tends to pi. Then the principal argument of f sub 1 of zeta, which is half the principal argument of zeta, will tend to pi over 2, and f sub 1 of zeta will tend to I times the square root of r. In contrast, if zeta approaches z equals minus r from quadrant 3, the principal argument of zeta will approach minus pi, and the principal argument of f sub 1 of zeta will approach minus pi over 2, and f sub 1 of zeta will now approach minus I times the square root of r. We get two different limits along two different paths, so that the limit of f sub 1 does not exist for negative real numbers, and therefore f sub 1 is discontinuous for negative real numbers. The difference quotient for f sub 1 prime of 0 equals f sub 1 of delta z minus f sub 1 of 0 all over delta z. F sub 1 of 0 is the square root of 0, which is 0. If delta z were to approach 0 along the positive real axis, f sub 1 of delta z would be the positive real square root of delta z. This simplifies to 1 over the positive real square root of delta z, so that the difference quotient will not tend to a finite limit, so that f sub 1 prime of 0 does not exist. So we designate the domain of f sub 1 as the set of complex numbers excluding 0 and the set of negative real numbers if f sub 1 is to be differentiable or analytic within its domain. Now we determine if f sub 1 is indeed differentiable within its domain. We write f sub 1 of z as u of xy plus I times v of xy, where u and v are real valued functions. If f sub 1 is to be analytic, then u and v must satisfy the Cauchy-Riemann equations. We also verify that the partial derivatives u sub x, u sub y, v sub x, and v sub y are continuous within the domain of f sub 1. These two conditions together will guarantee that f sub 1 is analytic. To verify these two conditions, if we are to differentiate this formulation of f sub 1, then we will need the partial derivatives of r and theta with respect to x and y. Differentiating r with respect to x, r sub x equals x over the square root of x squared plus y squared, or x over r, which is also equal to cosine theta. Differentiating r with respect to y, r sub y equals y over the square root of x squared plus y squared, or y over r, or sine theta. Now this time, differentiating this equation with respect to x, the left side becomes minus xy over the quantity x squared plus y squared raised to the 3/2 power. X squared plus y squared equals r squared, so we have minus xy over r cubed for the left side. And for the right side, we have the derivative of sine theta, which is cosine theta, to which we multiply theta sub x. Cosine theta is x over r. We cancel out some factors, so that theta sub x equals minus y over r squared. Differentiating the same equation, this time with respect to y, the left side becomes x squared over r cubed. We again cancel out some factors, and theta sub y equals x over r squared. We now differentiate f sub 1 with respect to x. Then we extract u sub x and v sub x from the resulting derivative. The derivative of the square root of r with respect to x equals 1 over 2 times the square root of r times r sub x. For the second term, we have the square root of r times the derivative of the exponential, so we have the factors e raised to the power I times theta over 2, I over 2, and theta sub x. Theta sub x is equal to minus y over r squared. We factor out 1 over 2 times the square root of r, and e raised to the power I times theta over 2. R sub x is cosine theta, and minus y over r is minus sine theta. Cosine theta minus I times sine theta equals e raised to the power minus I times theta. So that the derivative of f sub 1 with respect to x equals this quantity, which simplifies to 1 over 2 times the square root of r times e raised to the power minus I times theta over 2. Therefore, by applying Euler's formula, the partial derivative of f sub 1 with respect to x equals 1 over 2 times the square root of r times the quantity cosine theta over 2 minus I times sine of theta over 2. U sub x must be the real part of this derivative. So u sub x equals 1 over 2 times the square root of r times cosine of theta over 2. And v sub x must be the imaginary part. Repeating the exercise, but this time differentiating f sub 1 with respect to y, we have almost exactly the same terms. Theta sub y equals x over r squared. We again factor out 1 over 2 times the square root of r, and e raised to the power I times theta over 2. R sub y is sine theta, and x over r equals cosine theta. We factor out I and rewrite sine theta plus I times cosine theta as I times the quantity minus I times sine theta plus cosine theta. This is equal to I times e raised to the power minus I times theta. So that the derivative of f sub 1 with respect to y equals this quantity, which simplifies to 1 over 2 times the square root of r times I times e raised to the power minus I times theta over 2. E raised to the power minus I times theta over 2 equals cosine of theta over 2 minus I times sine of theta over 2. And multiplying this by I, the derivative of f sub 1 with respect to y equals 1 over 2 times the square root of r times the quantity I times cosine of theta over 2 plus sine of theta over 2. The imaginary part of this quantity must be v sub y, so that u sub x equals v sub y. And the rest must be u sub y, so that v sub x equals minus u sub y, and therefore f sub 1 satisfies the Cauchy-Riemann equations. We now determine if the partial derivatives of u and v are continuous. Let's start with u sub x and v sub y. Since z is non-zero, r and the square root of r are both positive, and 1 over 2 times the square root of r is a continuous function in x and y. Since we are excluding 0 and the negative real numbers, theta or the principal argument of z and theta over 2 are continuous functions of x and y within the domain of f sub 1. Therefore, cosine of theta over 2 being the composition of two continuous functions, namely cosine and theta over 2, is continuous within the domain of f sub 1. So the product 1 over 2 times the square root of r times cosine of theta over 2, and therefore u sub x and v sub y are continuous within the domain of f sub 1. Similarly, v sub x and minus u sub y, which equal minus 1 over 2 times the square root of r times sine of theta over 2, are continuous as is plus u sub y within the domain of f sub 1. Therefore, the partial derivatives of u and v are continuous. And along with satisfying the Cauchy-Riemann equations, we conclude that f sub 1 is analytic within its domain. F sub 1 prime equals u sub x plus I times v sub x, which is also equal to v sub y minus I times u sub y by the Cauchy-Riemann equations. U sub x plus I times v sub x is actually the partial derivative of f sub 1 with respect to x, so that f sub 1 prime equals 1 over the product of 2, the square root of r, and e raised to the power I times theta over 2. This part is f sub 1 of z, so that f sub 1 prime of z equals 1 over 2 times f sub 1 of z. F sub 2 equals minus f sub 1, so that f sub 2 prime equals minus f sub 1 prime, which equals minus 1 over 2 times f sub 1. Minus f sub 1 is f sub 2, so that f sub 2 prime equals 1 over 2 times f sub 2.